Hello students, so today we are going to discuss about nucleation. This nucleation is a first order phase transformation, and when a new phase is formed, an old phase whose free energy, by free energy that means we are talking about this delta G, free energy change, uh, has become higher than that of the emerging new phase, then this first order phase transformation of nucleation takes place. Now it has two different types. First one is called the homogeneous nucleation, uh, and the second one is called heterogeneous nucleation. Now, when all these nucleation process, the first phase is formation of little embryos. So say we have a solid solution. Here small embryos are formed, and these ultimately grow into formation of large crystals. Now the transformation requires the passage over a free energy barrier. So there has to be a free energy barrier, that is delta G, which needs to be crossed. Now the surface contribution to the free energy of the new phase is greater. So it has two contributions. One is delta GV. So we can see here delta G has two contributions. One is the volume contribution, that is delta GV, and one is the surface contribution, 4 pi r square, comma. The surface contribution is higher, and to find out the optimal or the barrier, we need to differentiate it with respect to r. So if we differentiate it with r, it comes out to be 4/3 by delta G, 3r square plus 4 by gamma into 2r. It has to be equal to 0 for finding out maxima. And by equating, we get the following two. This is the critical size of the nucleus, which has to be overcome for the embryo to grow, and this corresponds to the critical free energy change barrier that needs to be crossed for the nucleation to take place. So if we plot delta G versus r, so this is the surface contribution, 4 pi r square into gamma, and this is supposed to be the volume contribution. And so we take a mean curve of these two, then this is the barrier that we're talking about, and it is of course above towards the surface contribution, since surface contribution is found to be greater, and the corresponding critical size is the critical size. Now the heterogeneous nucleation, on the other hand, is based upon this Young's formula. So we have a solid solution, and we have a liquid, we have a solid growing, and this is the interface. So it is based upon this Young's formula. Gamma IL is equal to gamma SI plus SL cos theta. This is the angle theta. Now for the heterogeneous nucleation, this is the free energy change is comparatively less compared to the homogeneous nucleation, and these are the two different values. So here you can see R star is equal to, this factor is more prominent. So previously we said that it was only gamma, but now for homogeneous nucleation, this was for homogeneous. However, here we are contribution gamma SL. You can see that. And in the free energy change expression, a new parameter comes into the picture, which is called the shape of the nucleus. So the shape of the nucleus also becomes an important factor in case of a heterogeneous nucleation.